NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hello, and welcome to another edition of the 2022 Von Karman Talks. I am Nikki Wyrick from JPL's Office of Communications and Education, and I will be your host for our topic this evening, Curiosity, a Decade on Mars. Curiosity successfully landed on the surface of Mars August 5th of 2012. In the past decade, Curiosity, also known as the Mars Science Laboratory, or MSL, has exceeded expectations, completed some amazing science, and has so much more to give. Joining us as co-host this evening is Sarah Marcotte. Sarah brings over 2 decades of experience inspiring learning in out-of-school environments. Currently a public engagement specialist for JPL, she works to connect learners of all ages to current scientific research in person and online through events, exhibits, and virtual experiences. Hiya, Sarah.
Hey there. Great to be here tonight, Nikki.
Oh, we are so happy you are here. Now, you've got some resources to share with us as well tonight, so I'm going to throw it over to you to share some of those resources.
That sounds great. So I am so happy to be here tonight. This mission was the first one that I worked on as a public engagement specialist here at JPL. So it was my first introduction to what happens on Mars and the biggest, most capable rover that we sent to Mars. So it has a place near and dear in my heart. Now, I want to let people know how they can follow along with the mission. Of course, you've tuned in tonight to hear from 2 very important mission team members. However, there are times when you're at home and you want to see what is happening with the rover. So I would like to see the rover website. If we can pull up I want to tell you about the URL first. So the mars.nasa.gov/MSL for Mars Science Laboratory. That is your homepage. That's where you're going to get all the good stuff. Now, when I'm on that site, I learn about the rover, I see what's happening, there's a blog, so you can keep up to date with the science. But one of my favorite things on this website is the location map. So this shows where Curiosity is in Gale Crater and has been for the over 3,000 sols or Martian days that Curiosity has been exploring Gale Crater. So every time the rover drives, this map is updated with the location. Now, there's another neat thing that ties into this location map. So on the next graphic, you're going to see, actually it's a cute little video. This is called Explore with Curiosity. Now, this is real data. So both of these experiences are using real data from the rover. So when people drive the rover and it gets updated on that map and the cameras take pictures, it comes into both of these experiences. So you can see a CGI version of the rover in Gale Crater. That's all real data. And then on the left-hand side, look, there are all these pictures that the cameras took on any particular day. So I love those 2 things because I can always see where the rover is in Gale Crater as it's ascending up the side of a mountain. And then I like to see all the different cameras in the pictures that they took. So those are 2 great resources to follow along. And it's all using real data, and it hits the website the minute that the rover does anything. So that's what I wanted to share. And then, of course, I will be taking questions both of our speakers and after our speakers finish tonight. So have your questions ready in the social channels.
Thank you, Sarah. Those are some great resources, and I'm glad we have you with us, especially because of your personal connection to Curiosity. Sarah and I want to remind you that this is your space program, so please do get involved in the chat on those social media sites. And as always, if we do run into any technical difficulties or small failures, we ask for your patience tonight, and please stick with us. We will get them sorted out as soon as we possibly can. Now on to our first speaker of the evening. Dr. Ashwin Vasavada is a planetary scientist at JPL and the project scientist for NASA's Curiosity rover that began development in 2003 and successfully reached Mars in August of 2012. He now leads the international team of scientists as they explore Gale Crater on the Martian surface. He also has participated in the operation and analysis of data from several other NASA spacecraft missions, including the Galileo mission to Jupiter, the Cassini mission to Saturn, and the Lunar Reconnaissance Orbiter. He holds a Bachelor of Science in Geophysics and Space Physics from UCLA and a PhD in Planetary Science from Caltech. We are honored to have you with us this evening. Hello, Ashwin.
Hello. No, great to be here. I can't wait to talk about everything we've done in 10 years.
Oh, yeah. I mean, 10 years have flown by, I'm sure, but I want to start off with how you actually got to where you are. So, how did you get to where you are today?
As you heard a little bit in the introduction you just gave, uh, I went all over the solar system to get to where I am today on Mars. It all, I think, for me, really started when I was a kid, and I had a book that had a bunch of pictures about spacecraft missions that had gone to Mars and Jupiter before. And the picture that really caught me when I was little was one from the Viking lander on Mars, where a camera was just looking out over this vast landscape. And it just blew my mind as a kid that there's an entire other world out there, a whole planet that you could explore, with robots. And that's what I wanted to do from that point onward. And I didn't really know how to get there. I majored in aerospace engineering when I got to UCLA and figured out that actually I'm more interested in science than engineering, like understanding how things work and not necessarily building the things, to put it kind of in a simple way. But so then I switched to physics, and I still didn't really know how to get there, but I found a faculty member, a professor who was working on JPL missions, and that's how I learned how to actually get there. So I went to grad school to work on a spacecraft called Mars Observer, and that's when I learned my first lesson that, planetary science doesn't have guarantees. It's difficult, and what we do is very challenging, and there's a lot of risks, and things don't always go your way. And as I was actually driving my car to go to Caltech for my first day of grad school, I heard that the mission was lost. And I then worked on Galileo, on Jupiter for a few years, came back to Mars on another spacecraft that also failed to reach Mars. Tough game. And worked on Cassini for a few years, on Saturn. And then finally, I got this wonderful opportunity to work on Curiosity, which has made up more than enough for the disappointments I had earlier.
Well, I'm certainly glad that it has made up for the disappointments of earlier. You've been on this mission for a while. I mean, you really know the story of this. So tell us, what were we intending to find with Curiosity?
Sure. And because this is the anniversary celebration, I'm just going to kind of go all the way back and talk about why NASA wanted to fly the Curiosity mission in the first place. And we were charged with answering this question, was Mars ever habitable? You see this picture of Mars. Today, this is what it looks like. It has little wispy water ice clouds. It has polar caps that are made of water ice. But the one thing you see when you kind of compare in your mind how Earth looks versus Mars is there's no liquid water. There's no oceans. There's no lakes. But we have evidence that in the past there was. So we think in the distant past on Mars, it may have been a much more friendly place to possible life. So in the next graphic, let's talk about what it actually means to study habitability. So we're looking for three things, and we needed to figure out how to answer, how to explore for these three things on Mars. We wanted to look for persistent liquid water. We wanted to see if Mars ever had water that lasted not just for a day or a year, but millions or tens of millions of years, long enough that life could actually make use of it, and the slow processes like life originating and evolving could make use of that water. We also wanted to look for the key chemical ingredients of life. Life doesn't only need water, of course. It needs organic carbon. It needs other things like nitrogen and sulfur and oxygen and phosphorus, all the various elements that make up the biological machinery within us. We want to look if those raw materials were there on Mars. And finally, we want to look for sources of energy that could power metabolism, that could power life. There's sunlight, of course, like there is on Earth, but you can dig down on Earth and find places where life has managed to use the chemical energy within the rocks and soils themselves to power itself. And so we could look for those sorts of things on Mars as well. On the next one, we needed to find a place to go to ask these questions, to search for those things. So we spent about 5 years looking for kind of the perfect site where we could study habitability and have a chance of looking for those key requirements for habitable conditions. And we found this very special place called Gale Crater. It's a crater that's 100 miles across, but the very unique thing about this crater, it has a big mountain of rock in the middle of it. And that mountain isn't a mountain that was pushed up by plate tectonics. It's not a volcano. It's a mountain of sedimentary rock, meaning that over time, wind and or water brought in sediments and slowly built up the floor of the crater, which was then eroded into the shape of a mountain. What's significant about that is that that slow action of sediment going in the crater by either wind or water created a mountain that is composed of many different layers that built up slowly over time, and therefore are now a record of what the environmental conditions were like as each layer was laid down. And even more exciting, even before we landed, we could see from orbit that those layers were not all the same. Some had evidence of minerals that formed when water was present. Some had textures that were quite different from the others. So we knew that there was a geological record there to explore that would tell us how the environment was changing over time. And so by going through those layers, layer by layer, we could kind of read the history of Mars and figure out if any of those time periods had all those elements needed for habitability. So then, of course, we needed to figure out, well, actually, there's one more very special thing about Gale Crater. If you go to the next graphic, Mars was once, we think, much more of a Earth-like planet. You could say it was had a lot more water and maybe was even warmer, and then of course changed to the dry, cold desert planet is today. And maybe the first billion years or so of Mars history was when it had all this liquid water, we think, and then the last few billion years have been this cold, dry desert that probably wasn't too friendly for life. But a dramatic change happened sometime around 3 billion years ago, and that's exactly when those rocks were laid down in Gale Crater. So not only does it have this great history for us to explore, but that history is from a very dramatically changing time in Mars history. And so then we needed to figure out how to actually study that and to equip a rover to make these investigations about habitability. So on the next graphic, you can see that we have a car-sized rover. So one thing we figured out is that in order to climb this mountain, explore layer by layer, we needed to move. We couldn't just land in one place. We wanted to be able to look at all those different layers and ask at every moment in Mars history, was this a time that was friendly for life, potential life? So we have a rover that could drive, and we have 10 scientific instruments to help answer the questions that we were asking. But very importantly, we have a drill, so we can drill into rocks that make up Mount Sharp, deliver that powder to laboratories on board the rover that could tell us in detail what minerals are there and what chemicals are there, so we can understand whether there's organic carbon and what the minerals tell us about the environment that was once there. So we are now all set to go, and this has kind of set the stage for what we've done over the past 10 years.
Yeah, so tell us about that. I mean, it sounds like you had some very lofty goals and ambitions, and that's wonderful. But what did we actually find in the last 10 years?
Yeah, so it's been, I think, exceeded our expectations in every way, and that's just been wonderful. So let's get into that. On the next slide, we've now landed, and this is the view we had from our landing site. We had this gorgeous panorama that we took shortly after landing of Mount Sharp in the distance. But what was amazing about this is how far away Mount Sharp was. It looked so daunting at the time to think that we've landed. One person used to say that we were in the parking lot next to Disneyland, looking at Disneyland, from the parking lot, and we still had to get there. And we knew it would probably take over a year to drive there. So it was pretty daunting, but where that arrow is pointing is exactly where those very interesting layers were exposed on the side of Mount Sharp. And we wanted to get there over time. And if you go to the next graphic, we're kind of zooming in on that area. And even with our telephoto lens, it's still so small. But on the next graphic, you can see that in 10 years, we've made a lot of progress. We took about 2 years to drive to the mountain, partly because what we saw on the plains was more interesting than we expected. And then we spent about 8 years climbing through the layers of lower Mount Sharp, very systematically investigating layer by layer and looking for those ancient habitable environments at every step. And currently we're about where that star is. And we're at a very interesting site, which we'll talk about later, right where the mineralogy and the textures on Mount Sharp change very dramatically And we think we're right at the point where there's a big change in Mars' ancient climate that occurred. So let's talk about a little bit more specifically about what we found. And, when we landed, we first drove across the plains. And on the next slide, you can see that one of our early discoveries, which was super exciting and very kind of something you can just appreciate almost just by seeing it. We came across a whole bunch of rounded pebbles littering the landscape. And nature doesn't make round pebbles too easily. Round, rocks are jagged, they're angular. And one way that you can make rounded pebbles is that they're carried along in a flowing stream. And the rocks kind of grind against each other. And over many, many miles of travel, you end up with these rounded rocks. In fact, I once went to a home improvement store and wanted to get some rounded pebbles for my garden, and they're labeled, river rocks. And so we all kind of understand what this means. And to see those with our own eyes, with the rover's eyes, just made a big impression, because you can look at pictures of Mars' surface from space and see that there might be river channels, but to come across a bunch of rounded pebbles that were rounded in flowing water was amazing. On the next graphic, we then continued further towards the center of the crater and where the mountain is today, and we found evidence of where those streams once flowed into standing bodies of water. So if you kind of roll back history 3 billion years, the crater would have been empty. There wouldn't have been a mountain yet, but water was flowing in, carrying sediment that built up the mountain. And these layers that you see in this picture are where the streams entered standing bodies of water and made little deltas. So on the next one is when we got all the way to where the mountain is. And, we've seen now the stream, we've seen the delta where the stream meets the lake, and now we're in the lake where the lake was itself. And we saw that the bottom of Mount Sharp was composed of very flat millimeter scale layers of basically what used to be mud at the bottom of ancient lakes that's now turned into mud stone. And we didn't just find this at the bottom of Mount Sharp, we found it for meters and meters and meters and hundreds of meters above the bottom of Mount Sharp, meaning that the lakes persisted for quite a long time. And of course, as we drove up Mount Sharp, we took out our drill at every opportunity we could and sampled the rocks and did those detailed investigations of habitability. So on the next slide, you can see that we've now drilled 35 holes with the mission, and they're not all the same. Even from this picture, you can see that the colors are just amazing. And some rocks, for example, you can see are redder than others, and the material inside the rocks is redder, meaning that things are more oxidized. The iron in the rock has turned into kind of a reddish color. And other rocks are very gray inside, meaning that the oxidation that turned Mars into the red planet didn't penetrate deeply into the rocks, which is actually a good thing for finding evidence of ancient life, because oxidation can destroy that evidence over time in some cases. So, 35 holes, we've learned a lot. We've seen a lot of different things. And the next one is kind of a summary, coming back to our questions about what makes a habitable environment. Curiosity has found a lot of evidence that of water in the ancient past that was suitable for life. And what I mean by that is we found evidence that the water in these lakes in ancient Mars was not too acidic to support life. It was not too salty to support life. It was just the kind of water that life would need to flourish. And we've also seen that in these same lakes, there was organic molecules, organic carbon, and some of the other chemical elements that life needs. In fact, all of the main ones that life would need, and even evidence for nutrients that were in those lakes as well. And then we found different minerals that when paired together could provide those chemical sources of energy for certain types of microbes to use underground. So, really we've checked all the boxes in all these, in many of these different drill holes, especially the ones that come from these environments where lakes once were. We found really abundant evidence for habitable environments. So on the next one, honestly, I throw this picture into my talks just because it's one of my favorite ones of the mission. But what it does show, though, is that lakes didn't last forever. And so what you're looking at here are the lake sediments in the foreground and some really amazing buttes and mesas on the two sides. And what's on the top of these mesas are sandstones that formed when the lakes were gone, and dry sand dunes covered the entire area. and then those sand dunes turned into rocks. So what you would have seen then is those dark mesa tops connecting with each other and forming a continuous layer. But since then, a couple more billion years has gone by, and wind has eroded that sand layer away to where now there's just these buttes and mesas left over. But on the next one, you'll see one of my other favorite discoveries of the mission. One of the other most important discoveries of the mission is that habitability wasn't just present, at the surface where the lakes were, but was present underground as well. And this is really meaningful. I mean, because underneath everything we see at the surface, the rocks were forming, and then they were fracturing as they were being buried. And then groundwater flowed through those fractures and precipitated minerals along the walls of those fractures. And what you're seeing in this picture is now that some of that rock has been eroded, that softer rock has been eroded away. What's left are the white minerals that used to coat the inside of those fractures. And these are calcium sulfate minerals. But what this tells us is that water was circulating within these rocks long after the lakes disappeared and the mud they left behind hardened into rock. So whatever was happening at the surface, I think an even a longer story was happening below the surface. So on the next slide, here, let's see where we are. Was Mars ever habitable? And I think the mission has answered a resounding yes. And not only for a short period of time, but probably for tens of millions of years, and maybe even longer in the subsurface. So this is a great discovery for the mission, and really why Curiosity was sent to Mars. And I think it's exceeded all our expectations.
I mean, it's great to know that we've answered the big question, right? But that kind of leads into this next point. We've done so many great things, but what comes next? Where do we go from here?
Yeah, we are at a really exciting time in the mission. Even 10 years in, it has not gotten boring by any means. In fact, I think we're on the brink of making some truly astounding discoveries with the mission. Where we're at now is where this arrow is pointing. And look, this is that view from Sol 23 that I showed earlier that we were so far away from. And now we're actually where that arrow is. And we're right at that boundary from where the flat layers of lower Mount Sharp turn into these rounded hills. And these rounded hills we think are, we know from spacecraft measurements from orbit that they have a different mineralogy. They have these sulfate, magnesium sulfate minerals enrichment. They're enriched with these magnesium sulfate minerals, which we believe might be telling us that they formed in environments that were drier than the ones below. So we might be right at the brink of seeing, at the minimum, a dramatic change in Mars climate, and maybe even an end to the era of habitability. That's the thing we need to answer now. Did habitability persist through a dramatic change in the climate from the environments that were much wetter to environments that were drier? On the next one, look, here's where we are. This is something I always dreamed of. In those pictures from Sol 23, you can kind of look out in the distance and you can imagine that one day the rover was going to be among all these beautiful hills on Mount Sharp. And this is exactly where we are now. And so these are hills that kind of tower above the rover on all sides. And on the next slide, you can see that here's a cliff, a face that's just much taller, much bigger than the rover. We're driving next to it. Couldn't imagine we would be in such a fantastic landscape 10 years ago. And on this cliff face, there's all these beautiful colors where the groundwater that once flowed through the rocks has affected the minerals in this cliff face in different ways, causing some of them to turn red and leaving other ones in the more grayish color. It's just a truly fantastic landscape. And the next slide. Here's looking back now, so we can kind of look in the rearview mirror and see where we came from. And you can see we're pretty high up. We've gained over 2,000 feet in elevation after driving 18 miles. And we can look back and see where we came from. There's a crater floor in the distance and the wall of the crater in the very far distance. On the next slide, what's really special about this picture is this is kind of the reverse counterpart to that Sol 23 mosaic. And where the arrow is pointing is our landing site. It took until just recently for us to be high enough on Mount Sharp where we could actually look back and see all the way to where we landed. So I just, I'm just amazed that we can look back at that Sol 23 picture, dreaming of where we would be one day, and now we're there, and we can look back and see where we landed. On the next one, here I just want to tell you a little bit about what we're currently doing, what we're currently finding. We are definitely out of the era of lakes on Mars in Gale Crater, which is exciting. They lasted for a long time, but now we're seeing that the rocks around us no longer are those ones that formed in ancient lakes, but formed actually in dry dune fields. But that's not the whole story. So we're not completely dry yet, because those dark ridges with that left arrow are where streams once flowed among those dunes and deposited sand that was carried by liquid water, flowing water. So we're in kind of a dryish environment. On the right, you can see all these wavy layers that formed in dry dune fields. And on the left, you can see these dark ridges that formed in streams. On the next one, this is a self-portrait that we took recently in this area, and just wanted to show you what the rover looks like after 10 years. It's almost turning the color of Mars. A lot of dust has deposited on the rover. The wheels are kind of banged up, as I think everyone knows. We ran into some issues early on with holes developing in the wheels, but we've been very careful in how we drive, and I think we've managed to make the wheels last a long time. But the rover is doing incredibly well after 10 years. We really have all the capabilities we need to keep going further. And the last thing I'll just cover is about what lies ahead. So in the next one, we'll see a little animation of what's going to come up in the next few years. So in the foreground are some places we've already been, and then right about in the next few seconds is kind of where we are, which is right near where those rounded hills begin, and that magnesium sulfate bearing unit that might tell us about that dramatic change in Mars climate. Right above that, there's actually a channel that's been etched into those layers. So here you can see what looks like to be an ancient riverbed that's etched into those layers. So that's going to be exciting to see whether liquid water flowed even after the sulfate unit formed. Then we're going to drive and continue to look at that sulfate bearing unit until we once again head more directly uphill on Mount Sharp. Maybe this is in 3 or 4 years from now. And we get all the way up to where this very strange looking layer is. It almost looks like a lemon meringue top on Mount Sharp. And this layer isn't actually part of the continuous geological record. It was pasted on at a later point in time. So when we reach here, maybe in 3, 4, or 5 years, we'll have read the entire book of Mars history that's preserved in Lower Mount Sharp, and we'll have done everything we hoped we could ever do. So let's hope we get there.
Let's certainly hope so. And I mean, thank you for encapsulating 10 years of amazing science in just a short period of time. I do want to take a couple questions from the audience. I think we only have time for 2 quick questions. So I'm going to throw it over to Sarah, because I'm sure there's lots of people asking science questions in the chat.
Well, definitely a lot of questions coming in on the chat. So the first one I'm going to ask you, Ashwin, is from Mai on Facebook. Mai wants to know, what was Curiosity's most surprising discovery?
I'm sure there's been a lot of surprising ones, but I think the most surprising and profound one to me is that those lakes persisted much longer than we could tell from when we just had satellite images before we landed. We thought there may have been lakes at one layer of Mount Sharp where there was a lot of clay minerals. We found lakes at the crater floor. Then we found lakes at the bottom of Mount Sharp, and then those lakes persisted for several hundred meters of thickness, which probably translates to something like tens or hundreds of millions of years. So not only was Mars habitable and the lakes were there, but they persisted for much longer than we ever could have known.
Well, that is a perfect segue to my next question. It's from Gretel on LinkedIn. You're mentioning lakes. Gretel wants to know, where did the water go?
Yeah. Probably evaporated, and maybe some of it's now frozen at in the polar caps. But a lot of Mars water that's not still, in the polar caps or incorporated into minerals in the soil may have actually been even lost to space. Mars used to have a much thicker atmosphere, and some of that atmosphere and some of the water was lost to space, and a lot of the other water is now just in the form of minerals or ice.
Awesome.
Do we have
So
time for one more? No. Okay.
okay, Sarah, one more. You can throw one more in.
All right. I'm sorry. One more, because it's a question that I've heard before, and I think it's an interesting one. So, Manuel on LinkedIn wants to know how much radiation the rover is exposed to.
Yeah, I can't give you like a number or anything, but I can say it's more than you'd get on Earth because Mars has two things going against it. It has a thinner atmosphere, so it has less shielding from the atmosphere, and it also lacks a strong magnetic field, both of which help us on Earth not be exposed to the radiation that comes from cosmic rays, which come from deep space, or from radiation from the sun. And I'll just take the opportunity now to mention that we have an instrument on the rover that NASA specifically flew on Curiosity to measure that radiation at the surface of Mars in order to prepare for eventual human exploration of Mars. So we've been taking radiation measurements actually since shortly after launch. We measured radiation the whole way to Mars and then through the atmosphere and on the surface now for the last 10 years. We've even done experiments where we snuck the rover up next to one of those big cliff faces I showed so that we're blocking part of the sky, and we can measure how well that cliff face protects the rover from radiation coming from space. And therefore, if astronauts could use natural features like cliffs as shelters to protect themselves from radiation.
Well, I'm certainly glad I let that last question in because that's a question I've been asking myself. So, Ashwin, we are going to come back to you in just a few minutes. I want to take a moment now to actually introduce our second speaker. As Ashwin was talking about, Curiosity has done some great science, but a lot of it has been because Curiosity has been able to drive. So I want to introduce our second speaker. Keri Bean is a systems engineer at JPL, and she is the deputy lead rover planner, aka Mars rover driver, and robotic arm operator for the Curiosity Mars rover. She also worked on Curiosity as a student at the time of landing on the environmental science and MASTCAM teams. She's worked on numerous other missions, such as Ingenuity Mars helicopter, the Mars exploration rovers Spirit and Opportunity, and many more. She got her bachelor's and master's degrees at Texas A&M University in meteorology, with her focus on studying the weather on Mars. Hi, Keri. Thanks for being here tonight.
Hi, thanks for having me.
So I want to start off the same way. I mean, you both have great stories of how you got to this mission. So how did you get where you are today?
Yeah, so I grew up totally obsessed with weather. I was glued to the Weather Channel, and it was a huge part of my life. When I was 3 years old, a tornado hit my house. When I was in the 5th grade, I had to evacuate from a hurricane. And when I was in high school, I was struck by lightning. So it's always kind of a big part of my life. And so I didn't really get interested in space until high school, where my family was doing the whole Disney World vacation in Florida. We just happened to be there the week of a space shuttle launch. And it was STS-114, which was our return to flight. And even though we were miles and miles away, just you could feel and see the space shuttle. And I was like, okay, maybe this space thing is kind of cool. So I started reading a lot more, and I decided to go to space camp. And while I was at space camp, one of the documentaries they showed was Roving Mars, which was about Spirit and Opportunity. And I remember saying, hey, those Mars rovers are kind of cool. And I decided to go to school for meteorology and lucked out that I got to work with a professor who let me study the weather on Mars. If you pull up my first graphic, you'll see the professor and I, when we worked together on Curiosity, he brought me along to working on a whole bunch of different missions, including the Phoenix Mars lander, both Spirit and Opportunity, and then on to Curiosity. So I actually joined Curiosity first about a year before launch as part of the MASTCAM team and the environmental science team, working with Ashwin and all the other great meteorologists to get ready to study weather on Mars. So I was looking for clouds and dust devils and other anything meteorology related. And when I was ready to graduate, I luckily got a job at JPL. My first mission was actually working on Dawn in the asteroid belt. And so the asteroid people are great, but I miss Mars. So as soon as I could, I went back to Mars, and I went to Opportunity and was one of her final engineers. And I was in the middle of rover driver training for Opportunity when we lost contact. So in 2018, the Curiosity team said, hey, we're about to start another class of rover drivers. Do you want to come along? And so I was able to finally get my Mars rover driver license and work my way up to now being the deputy lead rover driver for Curiosity.
Well, Keri, it's very obvious that you're passionate, just like Ashwin, about Mars in particular as well. But you mentioned your rover license. How do you get a rover license?
Yeah. So it takes a little bit of time. So it usually takes like 1 to 2 years, and we start out with classes. So unfortunately, if you think once you're done with school, you stop taking classes, that is not true. You're going to keep taking classes. So we have a couple weeks worth of classes, and that includes homeworks. And then we have some hands-on labs. And then we run some training simulations. And being a Star Wars fan, I had to make a Star Wars acronym for them, PORGs, Practical Operational Readiness Gambits. And so I roast my trainees through some porgs, and once they're ready, then they actually get to sit on shift with the rest of the team, and they'll actually develop the commands and drive the rover and move the robotic arm around with someone double checking their work. And after a couple months, usually of doing that, then they'll get their driver's license. It takes a while. It's a big investment, but you know, there's a lot to learn for rover driving, so it takes a while.
Well, I mean, it sounds exciting. I know you mentioned before that as far as rover drivers, there's fewer rover drivers than there are astronauts in the world, which is pretty cool to be part of that elite class. So congratulations on your rover license. But tell us, what is a day in the life of rover operations?
Yeah. So if you pull up my next graphic there, so it starts out, you've got a lot of like scientists and a mix of engineers. So this is a picture of me from landing night with some of the amazing women scientists on the team. And you start out with all those scientists in the morning looking at all the images coming down from Mars saying, oh, you know, here's this cool rock, let's investigate this today. And then let's drive the rover over to the next rock. So if you pull up my next graphic, it shows a little bit about our process. So the scientists are looking at all that data coming back, and the engineers are looking at the health and safety of the rover. Did the rover stay warm enough through the night? How's the power situation looking? All that kind of engineering data just to make sure the rover's healthy. Then over the course of the day, the scientists and engineers will work together to make sure that we are getting as much science as we can out of the rover for the day, whether that's moving the robotic arm around, driving to the next location, taking pictures of cool rocks, any sort of data the scientists need. And then the latter half of the day, they'll actually sit there and write the code that will go to the spacecraft. We call them commands. And it's basically a laundry to-do list for the rover. So it'll say, do this, then do this, then do this. And then once we've written all those commands, we'll verify it, we'll run simulations, make sure it's all doing what we expect it to. And then we'll bundle all of that instructions up, and then we'll use NASA's Deep Space Network to radiate all those commands to the rover. And the rover will execute all of those commands for us. We usually send 1 to 3 days worth of commands at a time, but no live joystick for rover driving, unfortunately. Mars is just a little bit too far away to be able to talk to the rovers in real time. So we'll hear back from the rovers a couple times a day through our orbiter missions, like the Mars Reconnaissance Orbiter, Mars Odyssey, all those cool missions orbiting Mars. They'll send all of the data back for us. And then the process starts all over again the next day. We'll, again, look at all that cool data that came back and figure out what to do next.
I mean, it's incredible the amount of, both on the science and on the driving side, the operational side, how much connection and communication and teamwork this really takes. So, Keri, can you tell us, how have the past few years kind of changed things?
Yeah, so it's been really interesting over the last few years. None of us expected to be commanding Curiosity from our couch, and yet here we are. So if you pull up the next graphic, you'll see what it used to look like when we were all in person. So this is what it looks like in our downlink rooms. That's where all the engineering telemetry comes in, and the engineers are assessing the data. And then on the bottom, you can see what we call our uplink rooms. So this is all the engineers and scientists working together to figure out the next plan and make those commands. And for most of the mission, the science team has actually been mostly remote because they're working at other universities or other space agencies around the globe. And so we already were somewhat of a hybrid environment before, with all the JPL roles being at JPL. And then if you go to the next graphic, you'll see we all had to go from home. And so we brought all of our computers and our monitors. And one of the things for Rover drivers, we actually have really cool stereo glasses we can use, but we couldn't let people bring that home. So instead, I have to sit here and I put on my clip-on red-blue glasses and flip up and down and look in stereo, don't look at stereo, stereo. I look like this all day. It's pretty cool. We were working from our kitchen tables. I'm in the top left photo there, and you can actually see my cat underneath my monitors as well. Our pets have been very involved in, operating the rovers with us. But it's been very interesting to all be remote. And so now we're trying to figure out what those next steps are going to be of, how do we potentially work in a hybrid environment, and how do we bring people back safely? And it's really cool to be exploring this time and once again changing how we're operating the rover.
That is awesome. And thank you for sharing that, Keri. So I want to open it up for a few questions, because I'm sure we've had some questions online on the operational side. In fact, the chats are all lit up. So please keep asking your questions. But I'm going to toss it over to Sarah. We'll do 2 or 3 questions for Keri.
Sounds great. Okay. Next question is from YouTube. So this is from Akshay asking on YouTube. I heard Curiosity will be doing some autonomous navigation. Is that true? And how is that possible?
Yeah, so when we rover drive, we actually have a couple different ways that we can drive the rover. So we can be very, very specific with our commands of drive forward a couple meters, turn 30 degrees, go forward another couple meters. We can be very, very, very precise with what we want it to do. We also have all the way to the other end of the spectrum, we call it auto nav or auto navigation, where we can actually pick a rock or some other target in the distance and tell the rover to figure out how to get there itself. And it will actually take images, build a map, and we can tell it how brave or how careful we want the rover to be. And we will be able to drive the rover to those destinations that we may not be able to see. Is it safe to all drive there? Let the rover decide. So just kind of depending on what the goal is and how we feel, we can either let the rover decide or we decide.
Excellent. Okay. Next question is coming from Facebook. Christopher on Facebook asks, how fast does the rover travel on the terrain of Mars with the atmospheric pressure being slightly different? Does that have any effect on the rover?
Yeah, so not so much the atmosphere. Really our limitation is that usually while we're driving, we're tracking our position, and that takes a bit of brain power and time to think. And we don't go very fast. We only go about a meter a minute, and that's about 3 feet per minute. It's pretty slow. So, we're very cautious, but we'll drive for a couple hours at a time. So, we'll make some good distance, usually somewhere between 20 and 100 meters per day, depending on the kind of terrain we're in. And, how close the next cool rock is. So, yeah, we're not very fast.
But you have to be slow and careful because you've got a very precious rover. And of course, you want to make sure it lasts a long time. So Ayush on YouTube is asking, can you tell us about Curiosity's twin, which is in the Mars yard on Earth? So it sounds like this person has been following us a while.
Yeah, so one of the things that we do is we actually build kind of I say backup, but extra rovers here on Earth so we can test all of our stuff here on Earth before we send it to Mars. So if we're doing a new activity, we can test it all here on Earth because it's much easier to fix the rover here on Earth than it is on Mars. So what we'll do is we've got one rover that is almost a perfect duplicate. It tries to have as many of the instruments. It has the drill and the robotic arm, and it's full size. And that's the one that we can really use to test out drilling or anything else we would need. We also have one that is the weight here on Earth, what it is on Mars. So it doesn't have the robotic arm. It's pretty much just the wheels and the legs and a computer in the middle. And so we can use that one a lot more for our mobility and driving testing, because that one will act a lot more like it will on Mars, but here on Earth. So that's a great question.
Awesome. So I think it's time to open up Q&A for both of our speakers. So Sarah, what are they asking for both Ashwin? We'll bring him back to the conversation, and Keri.
Excellent. Okay, so Sociodad on Facebook is asking, this will be for you, Ashwin. Has Curiosity confirmed the presence of water in any state along its path of travel?
So the main way we've confirmed the presence of water is incorporated into minerals. So in terms of the rocks on Mars, we found a lot of clay minerals in rocks, and clay minerals have water bound inside of them. But geologically, we've also found, evidence that lakes once existed, but a long time ago. So we found indirect evidence for liquid water that once existed, billions of years ago. The other place we found evidence for water today is in the sky. So we found really beautiful, we've taken really beautiful pictures of water ice clouds in the atmosphere. So water is around today, just not so much in liquid form.
Okay. This next one I think is very interesting. This is from Crystal on LinkedIn. Ashwin, I would like you to answer. To the best of your knowledge, does Mars have the potential to become habitable again?
Oh. I think the most straightforward way to make Mars habitable is to bring a lot of equipment with us if we go there and make it habitable for ourselves. So right now, if humans were to go there and set up a permanent kind of station, we would have to bring our own environment with us. There's more exotic ideas about, you've probably heard about terraforming Mars and making Mars back into an environment where other forms of life could exist. That's a little bit more science fiction than fact at this point, but a lot of people have interesting ideas about how maybe that could happen.
All right, next one is for you, Keri. This is from Facebook. Muniapen on Facebook is asking, since Mars is super dusty, how are the camera lenses clean and taking those great pictures?
Yeah, that's a great question. So our hand lens imager, the Molly camera, actually has a cover on it. So when we're not using the camera, we actually have a nice little cover we put over it. And the Mars dust actually settles pretty straight down. So when we're not using the cameras, we actually point our head down. And so all of the dust kind of settles on the back of our head instead of on our camera lenses. So that works out pretty well to keep our cameras clean.
All right, let's see. This is a person who has a good, appropriate name, Estrella. This is from LinkedIn, and this is for you, Keri. Would you say Curiosity has performed beyond its expectations?
Yeah, absolutely. So we've operated well beyond our expected lifetime, and our wheels have held up great, even though we had a little bit of trouble with them at first. We've figured that out now. We just figured out how to drill again. We've had a couple drill anomalies all throughout the course of the mission, and that's one of my favorite things about working at JPL is we have a lot of great people here and a lot of really smart people. And so every time we're faced with a problem, we turn around and solve it. And so we can certainly keep on going.
Great. Next question is from YouTube. It's for you, Ashwin. This is from Peter. Peter on YouTube is asking, is there any evidence of plant life to have existed on Mars when she was covered with lakes and rivers?
Not that we've discovered. So we have found that Mars was a very habitable place. It offered conditions that could have supported life if life ever was present. And that's the result of, our detailed investigations. We found that to be the case for, maybe tens or hundreds of millions of years in Mars past. But we have not found any obvious evidence for life. And I say that it would be obvious because we're not equipped to look in a very detailed way for like evidence of microbial life that may have existed 3 billion years ago. That would be very hard to detect at this point in time mostly because microbes don't leave really great fossils behind. So we found evidence for habitability, no obvious evidence of life. But in the future, when we hopefully will bring back samples of Mars rock back to Earth, we can use the very best laboratories on Earth to do that extremely careful observation to figure out if there's any actual evidence that life actually took hold on Mars.
That is awesome. Unfortunately, that is all the time we have for questions today. I do want to give our speakers one final chance for their final remarks, so please do stick with us. Keri, I'm going to toss it over to you for your final words for the evening.
Yeah, so one of the fun things about working on this mission is that you do not have to be the absolute perfect 4.0 A+ student to be a rover driver. I actually failed my first calculus class in college, and I'm now the deputy lead rover driver. So, take your failures, learn from them, keep going. And if you pull up my last graphic, I think working with some of the amazing people on this mission is just fantastic. Recently, we had for International Women's Day, we actually had a shift where we tried to staff every single role with a woman. And I think that was really exciting to be a part of, to have such a really great, diverse team, and all sorts of backgrounds as well, and fun hobbies. We have some people that actually have music records that they've put out. We have pottery makers, we have board game geeks, all over the place. We're all super diverse, and we all come together for this love for this Mars rover and to keep going and exploring another planet. So, stick around and we'll have a lot more fun adventures coming up.
That's awesome. Thank you, Keri. And Ashwin, your final remarks.
Yeah, yeah. On the graphic that I chose, for these final remarks, you can see a picture of a poster that's down the hall from my office, and the tradition had become that everyone who works on Curiosity operations, signs this poster, and you can see that there's just hundreds of names on it. And now, with our 10th anniversary, it just makes me very grateful, and thinking back to the literally thousands of people who were responsible for designing and building and testing and flying the spacecraft to Mars, and then the hundreds of people who have helped operate it. An amazing fact is that almost all of the people operating Curiosity now were not there when it landed. We're on, our second and third generation of people running the rover. And that just goes to show that it takes so many people, and so many people have contributed to the rover's success, not only at JPL, but at other places around the country and in other places around the world.
I mean, it's incredible to think of the team that has done all this amazing work and who's here today. Unfortunately, that is all the time we have for today for our talk. It seems like, 10 years to wrap it up in such a short time. But I do want to thank our speakers for joining us this evening, Dr. Ashwin Vasavada and Keri Bean, for joining us to discuss A Curiosity, a Decade on Mars. Also, I want to thank our wonderful questions co-host, Sarah Marcotte, and all of you that are working behind the scenes to make this possible. To those of you watching online, thank you so much for taking the time to join us every month. If you missed one or would like to revisit any of our Von Karman talks from the past 5 years, they are available on JPL's YouTube page. And please do join us next month for Voyager 45 Years in Space. We will see you next time. Have a wonderful evening. Bye, everyone. Thank you so much.